Consider a mathematical function with the following formula. If I ask you to draw the graph of this function, the simplest approach would be to plug in certain values, get the output values, and try to see those points on the graph. You plug in more points, you see the densely plotted graph. If I cut the formula, now imagine a case when you don't have this formula. So this formula is not available to us. However, I'm giving you some information about this process. I'm saying you that I give you certain inputs and certain outputs, and you get the graph or the estimate of this function. Well, the approach would be to plot these points on the graph and just try to fit a straight line between the 2 points, and depending on how far these points are, it will give you the approximate estimate of the function in that part. You may also go for the quadratic fit or some other polynomial fit depending on the number of data points and how far they are. These are the ways to build the estimate of this function. So this is the polynomial or interpolation techniques. Is there some other way or some better way to do this? Now consider the case when instead of giving you multiple points or the information at multiple points, we just have a single point A. I call this point A and its value f of A. So this point has some value f of A. Now if I ask you to build the estimate of this function with just a single point information, what you can do is that you can draw a straight line. You can just sit at that point for all the inputs. That would be a straight line which is just staying constant for all other values of the function. You may also give a random function or straight line, but you don't know how to tune the slope of that straight line. So the best approach would be to give this constant value for all your inputs. You want to ask me what should be the value of this function at some other points. I give you the same answer which I have. So this estimate serves at least better around this point. Now suppose I give you information about this function. So I give you f of A, I also give you f dash of A, I also give you, so let's consider these two things. Now you know that what the derivative gives you, it gives you the slope of the tangent at that point. So we can have a tangent at this point and we can get slope of this function at that point. Now we can extend this tangent line and we can add the intercept this point. It's already passing through that point. So we can build an estimate of this function, yellow curve, with this line which has some slope, and it's matching to at least the trend of the function at that point or in some neighborhood. If I give you some more information, let's say I give you second derivative of the function at that point, what you can do is that you can build a quadratic approximation of this function, which would be a parabolic kind of thing, and it will give you a good estimate of your function in some neighborhood. So how do we mathematically write this? So I am building an estimate of my function with this information. So I denote that with f hat of x initially was just giving me f of A, f hat of x when I included the new point, the slope. So I got I have the value of my function like this, f value of f at A and x minus A, f dash of A. So you can build the second order approximation of your function, which will be f of A plus x minus A, f dash of A plus x minus A square by 2 factorial f double dash of A. So you have some approximations of your function, and you'll see as you include more and more terms, your function starts to approximate very close or very well to your original function. This is the Taylor series expansion of a function. By just knowing enough information about the function at a single point, you are able to reconstruct a good approximation of your function. So there are several approaches to build approximations of function. This is what we do mostly in engineering problems. You get some readings, you try to build a model, or you try to reconstruct the governing equation of the system.